Let's talk about delta G and the cell potential. How are they related? If you recall, when we talked about the second and third law of thermodynamics, we identified delta G, the Gibbs free energy, the change in the Gibbs free energy associated with the reaction, as the maximum amount of useful work that you can harness from a spontaneous process. Remember, we said, in particular, if you have a reaction that incurs an entropy debt, okay, yeah, and if it's capable of releasing energy, part of the energy has to be released as heat to compensate for any entropy debt, and the rest of it, you can harness to do useful work. It doesn't have to be wasted as heat. And this is one way you can harness that energy. You let it run through. You let it drive electrons through a wire. You do electrical work. Okay. So imagine you have a galvanic cell that's discharging. Let's say a mole of reaction occurs. That means n moles of reaction will be transferred from the anode to the cathode. And let's just imagine that throughout that process, the cell potential, the voltage across your galvanic cell doesn't change significantly. Okay, so um, throughout that process, then you say delta G would be the energy that the electrons will gain when they travel without resistance from the anode to the cathode. And so that's just given by the charge. Okay, so n moles of electrons times the charge per mole. Okay, so negative n moles times negative F would be the total charge transferred. Okay, remember the Faraday constant is a charge per mole, the absolute value of the charge of 1 mole of electrons. Negative F is the actual charge since electrons are negative. So negative NF right here is the charge of the electrons, transferred, the n moles of electrons transferred. Multiply that by the voltage, that gives you the energy that the electrons will gain. Okay? So we did a similar calculation like this earlier, right? In the last lesson. So if electrons are passed through a resistor, then the energy that these electrons gain will just be dissipated as heat. You get your resistor to warm up, okay? Now, if you pass it through a motor or a light bulb, then you're able to convert it into something useful. So a motor, for example, you can use it to lift up an object. Okay, you can have it turn a motor. So delta G then we say is equal to negative NF times the cell potential. Okay. So that's the significance of the cell potential. It will tell you how much electrical work you can derive from your redox reaction that's happening in your battery, in your galvanic cell. Now, a AAA alkaline battery has a cell potential of 1.5 volts, okay? And a double A, I'm sorry. Same thing with a AAA. So if you measure the voltage across the positive and negative terminal of your battery, it's going to be 1.5 volts. And these are the reactions involved there. So zinc plus 2 hydroxide gives you zinc hydroxide plus 2 electrons. That's oxidation at the anode of your alkaline battery. And then in the cathode, the reaction is manganese dioxide plus water will give you MnOOH, that compound right there, plus 2 hydroxide. Okay, so those are the two half reactions that occur in your alkaline battery. Now, let's say you're going to use that alkaline battery to lift a 10-gram object. So you let it run a motor, okay, and the motor turns a pulley, and the pulley lifts an object, a 10-gram object, to a height of a half meter. So we have a 10-gram object here. You lift it up to a height of a half meter. How much zinc would be used up in the anode? Okay, and if all this happens in 5 seconds, let's say it takes 5 seconds to lift up the object, how much current went through the motor? So here's the series of calculations you're going to do. First of all, you're going to need to figure out how much energy do you need to lift the object. The work that you need to lift an object is equal to force times distance. Remember? Formula for work is force applied over the distance. So force times distance. And what force will you be applying to your object to lift it up? It should be on average, okay, to go from one height to another, okay, the average force you're going to be exerting would be equal to the weight of the object. The force of gravity is mg, right? So mg times the height And mg is the mass times acceleration due to gravity. That's the weight of your object. So what's our work due to lifting then? What's the mass of our object? 10 grams. So let's put that in kilograms so we have everything in SI. So 10.0 times 10 to the negative 3 kilograms is a gram, right? 10 to the negative 3 kilograms is a gram. Remember, 10 to the third is, kilo is 10 to the third. So 10 to the negative 3 times 10 to the third is 1, okay? Acceleration due to gravity is how much? You remember from physics, physical science? 9.80 meters per second squared. And our height is half a meter, 0.500 meters. How much work would that be? An answer for me? 10 times 10 to the negative 3 is 0.01, right? Times 0.01 times 9.8 times 0.5, 0.049 joules, okay? 0 kilogram meter squared per second squared is a joule. That is the work that you need to do, okay? And what is this work going to be equal to? That's going to be your delta G, right? So that's equal to moles of electrons transferred, okay? So that's the charge transferred times, okay, let me see, moles of electrons transferred times the Faraday times the cell potential, okay, minus NFE. So we can solve for moles of electrons transferred. What's our N here? N would be equal to 0.0490 joules over, and let's just use absolute values here. So Faraday is 96,500. That's coulombs per mole of electrons, okay? And our cell potential is how much? 1.5 volts. So 1.5 joules per coulomb. 1.5 volt is a joule per coulomb. A volt is a joule per coulomb. It's energy gain per coulomb of charge, okay? So coulombs cancel out, joule cancel out. That gives you the actual moles of electrons that are transferred, okay? So what would that be? 0.049 divided by 96,500 divided by 1.5, and you have 3.38, 3.39, 3.385 times 10 to the negative 7 moles of electron. Okay? Now, that's the actual moles of electrons for the lifting. Okay, that's not the moles of that's not the same N we talked about in our balance equation, because in our balance equation, if you have a mole of electrons, if you have a mole of reaction, that involves a transfer of 2 moles of electrons. So you can see from here, okay, you're transferring 2 moles of electrons for every mole of zinc that's involved in the reaction. So we can now calculate the moles of zinc involved. We can say moles of zinc equals 3.385 times 10 to the negative 7 moles of electrons times 1 mole of zinc is going to be consumed for every 2 moles of electrons transferred. Okay? So that, how many moles of zinc would that be? Divide that by 2. That should be 10 to the negative 7, right? So divide that by 2. That gives you 1.7 times 10 to the negative 7. 2 sig, if we 1.70 times 10 to the negative 7 moles of zinc. Okay, so that's the answer. 1.7 times 10 to the negative 7 moles of zinc. Right? So if all of that happened within 5 seconds, how much current is passed through the wire? What's the definition of current? Current is charge per unit time. Okay, so total charge that's transferred per unit time. So what's the total charge? Our current, this current right here, is NF, the total charge per unit time, right? And our time is how much? 5 seconds. And how much charge did we transfer? 96,500 coulombs per mole of electrons. By how many moles of electrons? 3.385 times 10 to the negative 7 moles of electron. I need some room. Let me redo this. So our current is 3.385 times 10 to the negative 7 moles of electrons multiplied by 96,500 coulombs per mole of electron divided by 5 seconds. Okay, moles of electrons cancel out. That gives you coulombs per second. What would that be? So this times 2, that was your moles of electrons, right? Times 96,500 divided by 5. That gives you 0.00653. Okay, so 0.0065 coulombs per second. A coulomb per second is called an ampere. Okay, so that's 1 ampere. So that's a unit of current. So our current here is equal to 0.0065 amps, or 1, 2, 3, that's going to be 6.5 milliamps. Okay, so that's the current that motor is drawing from your battery in order to lift that 10-gram object to a height of 0.5 meter.